Okay, thank you. Okay, so this is the plan for today. So some unfinished thing from last lecture. So I quickly ran through two aspects of like assessing machine learning algorithms and some important issues when you are developing machine learning models. Then followed by, we will be starting off with regression and classification, basically supervised learning techniques. So standard regression, linear regression, locally weighted regression, and if time permits, then we will get into some concept of classification. Okay, so some issues in machine learning, and this is in continuation with what we had been talking last time. So when you are designing machine learning models, what are the issues that you need to keep in mind? Okay. So number one is that what algorithms can approximate function well and when. Okay. So machine learning mostly about function approximation. So like how to approximate these things, when it can approximate the functions, some assumptions about the data, about the functions and optimization techniques, those things need to be considered. Second, how does number of training examples influence accuracy? Often we know that the number of training examples have some positive correlation with the accuracy and the model's capability to learn things. So that also you need to figure out. Then the hypothesis complexity. So essentially we are basically searching for this is a hypothesis space, and from which we are searching for a particular hypothesis which will suit our requirement. So the complexity of the hypothesis and what would be that, and how that is actually going to impact the final learning. Okay. Now noise is another very common thing in real data. So the question is, how does noisy data influence the accuracy? Okay, so this is another important consideration. Then, of course, the theoretical limits of learnability. Okay, so building a model is not enough. So you need to give some kind of performance guarantee. Okay, telling that okay, so given that this kind of data distribution, or so what this model can actually do, how much this model can actually learn. Okay, so that depending upon that, you can actually determine whether you should apply in a particular situation or not. Okay. Sometimes the prior knowledge is typically used in a model in building a model. So how can actually you use the prior knowledge to help building the model? Okay. And the other thing, this is not very common, but still it is important, that how can systems alter their own representations? Okay, so representation learning is like what representation would be good for the application that you're targeting for, and so over time, depending upon the changes in the data and changes in the requirement, whether your system can actually alter their own representations. Okay, so these are some of the factors that one has to keep in mind while dealing with machine learning algorithms. Okay, now the assessment of learning algorithms. Okay, so all about knowing how good your machine learning model is doing. Okay, so the most common thing is accuracy, percentages of correctly classified samples. So if it is classification problem, classified samples. If it is regression problem, then you basically want to measure the amount of error. Okay, something like squared error or something like that. You see that the number of examples needed to learn the model, and also the computational tractability. Okay, because some learning algorithms also build the model, some learning algorithms will require lots of computing power. Okay, to kind of give the good parameter estimation. So that is also another consideration while you are building model. Robustness. Some models are. Sorry.
What is computational tractability?
So computational tractability in the sense that so when, for example, think about, say, let me give you a specific example. Say you are building a neural network, okay, and so you can basically come up with the architecture, but then you have to estimate the model parameters, the weights and biases and all. Okay. Now, how quickly or how efficiently you can estimate those parameter values from the data itself? Okay, that's computational tractability. Okay, if the learning algorithms that you are using to estimate the model parameters is very complex, then it's difficult. Okay.
Yes, sir.
Okay. So robustness is one of the most important desirable criterion to assess the machine learning algorithms. So robustness against noise. So you build a model, but then if you notice that with some changes in the data, if your model performs very poorly, then the model is not robust. Okay, or some noise in the data, the model performing very poorly, then you can say the model is not very well. So the robustness is another important condition. Okay, for at least for real life setup. Representational complexity. Okay, so you can build a model, you can train the model, but then once you train this model, then you have to basically store this model somewhere, because when you are testing on test data, then you do not need to, you are not going to again retrain this and so on. So I'm going to reuse this trained model, okay, for inference. So how easy to store this trained model? Okay, how much space it is going to take? What is the inference complexity? Okay, in order to infer, for example, predict a particular samples, the level, output level, how much time you are going to take, and so on and so forth. Okay, and another interesting thing is transparency. Okay, this is of late one of the most interesting research topic, the comprehensibility for human user. So most of the machine learning models are non-transparent in the sense that it is difficult to tell that why a particular thing is happening the way it is happening. Okay, so unless you know that, in some of the safety critical applications, okay, for example in healthcare or in aircraft flying or automated driving, in these places where safety is absolutely important, it's difficult to apply machine learning algorithms. Okay, so transparency essentially to telling that, okay, whether I can decode what the model is actually doing. I know why this model is doing, which particular situation it is doing, so that I understand when it fails, why it fails. Okay. Okay. So these are some of these, the assessment of learning algorithms, some of the factors that you have to consider when you are doing these things. Okay. All right. So let's start with our discussion, supervised learning, and we start with regression. Okay, so regression is like probably the simplest, one of the simplest form of supervised learning. So quickly, this is kind of a pictorial view for supervised learning. All you do, basically you have a training data with features and output levels. Okay, so, and you have a learning algorithm, so which basically learns the function f, and then you map input data x to output level y. Okay, so that's what I want to do. So the learning algorithm takes the training data with all the features and output levels, and your objective is to learn f. Okay, that's basically more or less the pictorial view of machine learning algorithms. Now, not all machine learning algorithms are of parametric nature. For example, say when you are doing k nearest neighbor, you are not explicitly learning any function. Okay, but for example, when you are doing logistic regression, you are learning a function. So not always that you are learning a function, but often most of these cases, the neural network, support vector machine, or this or that, basically you are learning a function from the training data. And a particular learning algorithm that I use, that is used to learn the function, that will take the input data x and produce the output level corresponding to the input data. Okay, so that's the setup for general setup for any supervised learning. Okay, so broadly, two major type of supervised learning: regression and classification. So when the target variable which you want to predict is continuous in nature or is very large in numbers, okay, for example, in few thousands or in millions and so on, then you can actually use regression. Okay, for example, but often the general setup is that this output variable is continuous in nature. So here is an example that you want to predict the housing price, for example, okay, or you want to predict the exam grade, okay, from the previous data of how many hours you have studied and your previous performance and so on. So these are the kinds of variables that you consider continuous valued variable, and regression is a good fit for this kind of thing. Okay. In contrast, in classification, what we do, we have the discrete levels, okay, categorical values as the levels, okay. So, and it is small in numbers compared to, of course, the number of possibilities in regression tasks. So whether a given news article belongs to sports or politics, or you want to predict whether somebody is going to drop out of a particular college depending upon his previous performance or behavior. So something like this is basically you can do using classification. Okay, so number of possibilities are limited, and the number of the possibilities are essentially discrete in nature. So once you get the data, you have to determine that whether I should go for regression or for classification. That's the first task.
Sir, why the exempted prediction is regression?
So, so grade in the sense that I wanted to mean the CGP actually. So there's kind of slight mistake in this. Not the ABCD, but this CGPA. Okay.
Yes.
It's because CGPA is continuous in nature. Okay. Any other question? Okay. All right. All right. So yeah. So here is an example of regression problem. So you have, say, class attendance, you have hours of study, you have your current CGPA, and you want to predict your future CGPA. Okay. So that is clearly you can know that the target level is continuous in nature, and so this is a good fit for a regression problem. Okay. All right. So regression, what's the objective? And this is not only objective for regression, general for any kind of machine learning. Okay, so objective is to learn a function from input to the output, okay, using the training data. Training data essentially will help you to learn the function. So the regression could be linear function or non-linear function. So as you can see from this figure, linear function means basically straight line, plane, hyperplane, and so on. Non-linear function, as you know, if you increase the degree of the polynomial, you are going to get curves of different natures, very non-smooth curve, quadratic curve, and sine curve, and all kinds of stuff that you're going to get. So these are all non-linear regression. Okay, so it's essentially distinguished by the nature of the function that you are modeling. All right. So let's start with, and this is a simple, very simple form of regression, and I'm using this to introduce the basic concept of any kind of machine learning. So how the machine learning algorithms are actually developed. Okay, so this idea you could actually use for any other machine learning problems. Okay, so in general, that's the purpose that I'm going to show you how things are actually done. So in linear regression, for most of these cases in models, when you are dealing with machine learning models, you make some assumptions about the model. Okay, often. Okay. So it's difficult to come up with a model which is foolproof, which is assumption free, okay, which learn exactly the same function that the data is actually telling. It's difficult to do that. So in order to simplify all these things, we often make some assumptions. This is true for all machine learning, okay, or rather most of the machine learning algorithms. So here, linear regression, that assumption is that the function that we are trying to approximate or trying to find out is a linear function, okay, the polynomial of degree 1. So that means straight line in 2 dimensions. If you have 2-dimensional feature vector, it is a straight line. If you have 3-dimensional feature vector, you have a plane, and if you have more, then this is called hyperplane. Okay, but the equation is a polynomial of degree 1. That's the assumption. Now, what's the mathematical form of that? Because we are dealing with a mathematical equation, so we need a mathematical form of that. So for single feature, you have something like this: theta 0 plus theta 1x, and you are familiar with the equation of straight line. This is equation of straight line actually. Okay, that's what you have done in your +2 level. Okay, so here the theta 0 and theta 1 are the parameters of this model. Okay, or the straight line coefficients that you know. So when you have 2 features, then you have theta 0 plus theta 1x plus theta 2x. Okay, and when you have n features, you have something like this. So coefficient, one coefficient for every variable plus the another variable called theta 0. So this is the kind of standard form for linear regression. Okay, So all these theta zeros, theta 1, theta n's, these are basically called the model parameters. Often you know in machine learning that model parameters. So these are the parameters in this model, which you really need to estimate in order to get the model fully. Okay. So here is this more specific example. So you have the living area in feet square, then you have price in dollars, okay, and then the one possible linear regression function would be that y is equals to theta 0 plus theta 1x, where y is the price, which is the target variable you want to predict, and x1 is the living area, okay. And so when you only know living area, you really want to predict the corresponding price for that living area, which is probably you can use for housing markets and so on. Okay. Now similarly, if you extend a little further, then we have the living area, and then we have additional feature called bedrooms, and then you have to predict the price of that. So all you need to do, you need to extend this model a little bit from one variable to two variable, so you can get this equation theta 0, theta 1x plus theta 2x. Okay, so this is the simple example of very simple real life problems for linear regression. Right? So far so good. No issue. We assume that the function is going to be linear in nature. So the big question is how to get this actual model. So if somebody gives you data and you have to predict this output, you need to know the values of theta 0, theta 1, and theta 2. Because x1, x2 will be given to you because it's the input variables. But the model parameters theta 0, theta 1, and theta 2 unknown to you, you have to estimate. And the only thing that you can make use of is the training data that somebody given to you, where you had all these x's, x1, x2, x3, etc., and also the corresponding y values as well. Okay, the output thing. And so this you use this training data to estimate this model parameters theta 0, theta 1, and theta 2. Okay, that is more or less often the route that we take in machine learning. Whether you apply it on SVM, support vector machine, whether you apply this on neural network, you build first the model, that means figure out the structure of this equation or expression, mathematical expression. Then you know a bunch of parameters that you have. Then the next step would be estimate these values of these parameters. Okay, so the same route. Okay, now often most of the time we spend, at least the guy who developed any particular learning algorithm, most of the time he spends on like figuring out what would be my learning algorithm which will reliably predict these model parameters. Okay, that is one of the most complex thing in any new machine learning algorithm. Okay, so here also, so we need to define, in order to get that, we need to define an error or performance function of the model on the training data, right? So the error and performance function will tell you how well the model is actually doing. Okay, given a particular configuration of the parameters, how well the model is actually doing. If it is not doing well, we have to do something else. If it is doing well, then you can stop. Okay, so the performance error function will need to be designed first. Okay, so let's look at what we can do in this particular case, in case of linear regression. So let's focus on only single sample. So if I have a single sample in my training data, what this performance function will look like. Okay, so in my case, it would be yi. Here I means the ith, the level of the ith sample. Okay, yi is the output level of the ith sample, not the power. Okay, so don't confuse between these two. So in this case, my error function is yi. That means the target level of the ith sample minus my function, the function that I have constructed, linear regression function, and xi is the corresponding input, and so it's basically square of that. Okay, so that is my error function for a particular sample. Okay, and my objective would be to minimize this error. So how I can adjust the model parameters, that means parameters of function f, so that I can get zero, that's my desirable, zero error or minimum amount of error. Okay, all right. So as you know, these are the description of these things: target level of xy, model predicted value, and so on and so forth. Okay, so now because in any training data you have many such examples, so we need to define total error, because we want to measure the performance of the machine learning model on the entire training data set, not on a single sample. Okay, so we would like to define the total error. So the total error is defined as something like this. You simply take sum over the individual errors. Okay, and that is basically the total error, where n is the total number of samples in your training data. Now here the error function that I have taken is called squared error. Now over time during this course, you will know different kinds of error functions and objective functions. So when you know SBM, you will have different kind of error. When you know neural network, there you will have some other kind of error functions like cross entropy and things like that. So many kinds of error functions are there, very common in machine learning literature. So you get to know gradually. But this is the simplest, one of the simplest form of error function. Okay. So the total error is basically this individual errors, and then you sum them up. Now, so this is my error function, no doubt. Now what you have to do in order to find out, remember that my ultimate goal is to figure out these parameters, the values of these parameters, theta 0, theta 1, theta 2, and whatever you have. Okay. So what my objective would be, this is because this is error function, so I have to minimize ET with respect to this model parameters. Okay. So what would be my model parameters so that I will have minimum amount of error on the training samples. Okay, that's what I want to do. So for the time being, I am leaving this optimization part. So we will use a general method called gradient descent. Okay, which is like is a general purpose technique for optimizing any continuous function. Okay, or even with finite number of discontinuity too, you can use that gradient descent, which we will get to know later on in great detail because this is the fundamental of the modern deep learning. But so for linear, at least for linear functions, you actually do not need gradient descent because you can simply take the derivative, partial derivative with respect to thetas, and then you can actually get the closed form solution very easily to get the global minimum because this is a linear function. But for non-linear function, global minimum is not guaranteed often. So the preferred method is gradient descent, which we can use to find out like the minimum value or maximum value, whatever. Okay, so of function. So which we will get to know soon enough. All right. So this is how. So first model construction, followed by number of parameters. Then you basically come up with the corresponding error function or objective function, and then the optimization of error function with respect to the model parameters. And so you basically choose an optimization algorithm. Okay, and then find out the model parameters, and basically you are done. So that is more or less the roots to develop machine learning algorithms. Of course, there are complexities in between depending upon the complexity of this model and your target, your objective, and the nature of the problem. But this is more or less the general steps that you follow. All right. So just a small quiz for all of you. It's very simple. So for samples with 10 features, how many parameters ET will contain?
11.
Yeah, it's 11 parameters.
11.
Yeah, okay. Yeah, okay. Okay, all right. So what is the limitation of linear regression? Okay. So and so these limitations actually are limitations of many machine learning models, including linear regression. So this is called underfitting. So what it is underfitting? That the model fails to capture the structure in the training data. Okay. So for example, you had training data something like this. The black dots are your training data. Okay, X and Y you have. Y is the output level, X is the input variable, and so on. And so if you try to feed this model, feed this data using linear regression, you will never be able to do reliably because the plot itself telling you that this data is not quite linear. Okay, so you will be in trouble if you do that. There will be lots of error. And this problem is called underfitting. Okay, so this is a general problem for many machine learning algorithms, not only for linear regression. Okay, when you are not fitting the data as well as you had to fit this particular data. Non-linear regression. So you basically increase this degree of this polynomial. Of course, there you also going to increase the number of parameters as well. So here are some examples for the non-linear regression. Okay, you can see that 2 variables, 3 variables, whatever. So you can do that. Number of variables will increase, the polynomial degree will increase, and you can basically model curves of different complexities, quadratic, sine curve, etc. etc. What's the drawback of nonlinear regression? Again, one, of course, you have to determine that what will be the value of n, where to stop, okay, because you do not know a priori. So kind of trial and error you have to do on the data. And again, even for the same problem, if the data changes, training data changes, it may also change. So it's a slightly tricky to do that. Okay. Now, large value of n means the degree of the polynomial means also too many parameters. Okay, too many parameters means very slow to train the model. Okay, so these are some of the common problems. Okay, but the more serious problem is the overfitting problem. Okay, again, this is general problem not only for regression, for many machine learning problems. So in overfitting, what happens is that the model simply remembers the training data. It doesn't learn the pattern. Okay, it simply remembers the training data as is in the data. It's like a table-like thing. Okay, you have a table, look up, and you basically find something on the table. You say, "Oh, I found this." If you didn't find it in the table, you say, "Oh, I do not know this," something like this. You will never learn anything. Okay, so therefore, it doesn't have a good predictive power. Okay, so here is a classic, simple illustration of overfitting problem. That there are a bunch of points. And as you can see, it is difficult to kind of model this data using a regular curve. But if you by increasing the degree of the polynomial, okay, you can basically fit the all the data points in the training data set, which is not a good thing to do. Okay, often. All right. So, okay, so far so linear regression. So you have seen some problems with the linear regression. Okay, so there is a problem with the underfitting primarily. Okay, overfitting, although is a problem for non-linear regression, it is not a problem for linear regression because by increasing the polynomial, you can actually get very highly non-smooth curve. Okay. Now, so what we can do about it? We know that linear regression has a problem, although it is very simple, and so on and so forth. Non-linear regression also has a problem. So what we can do with this, and so on and so forth. So what is the solution? Okay, to address some of these problems. So the solution, I would say, is not the foolproof solution, but a relatively better solution is called locally weighted regression. Okay, and as the name suggests, the regression is basically done through local weighting of the samples. So let's look into it. Okay, so let's start off with the basic idea of locally weighted regression. So basic idea is that to predict the output for a new sample, because test sample doesn't have the output level, okay, and you have to predict the output for the sample. So you do the following. What you do? You take the training samples close to the test samples. Now you have a bunch of training samples in your data where the output value is actually known. And for the test data, you have the input variables, but not the output variables. So using these input variables or input features, okay, we basically figure out that which are the training samples close to the test sample, okay, based on the input features. Now, then what you do, you use the selected training samples to fit a linear function. Okay, you are not using the entire data set, entire training data set to fit the function, unlike linear regression. You are only selecting a few samples which are close to the test sample. You are only using those samples to find a linear function or linear regression curve. Okay, and so then basically you use this particular function to predict the output for test sample. Okay, so three simple steps you can do, and here is an example. So say you have the black dots are the training samples that you have in your data. Okay, and the green one, so the blue one, the bigger one, the test sample is the one for which you want to predict the output for. So what we do, we try to figure out the training samples which are close to this test sample by some similarity measure. We will get to know in the next slide how we do that. But for the time being, assume that there is some similarity measure or distance measure. You use that to figure out some close samples of that. Now, you basically use only those samples to construct the linear regression function, the linear function that you have, and train the model, get the parameters, and then basically you are done. So you are basically not considering other examples to build this model. Okay. So basic assumption is that when the samples that you are using is very close to the test sample, okay, they will have a very linear kind of behavior, very similar to each other. So this underfitting thing can be avoided. Okay, so that's the basic assumption.
Sir, are we splitting the training data into two parts? I mean, one part is to predict the function, and the other part is to check whether it is working or not.
So for a test sample, you do not do that, because for a test sample you simply pick out some examples from the training data and then do it. But for validation purposes, that how well that your model is actually doing and so on, there are some hyperparameters that you need to tune, which you will see later on. You need to do kind of this kind of validation. Yeah. Okay. Any other question? All right. Okay. So what are the key issues in locally weighted regression? So the key issue is that, number one, how to select the samples closed to the test sample, because these are the samples which are going to determine everything for you. Okay, so how to select them? Okay, so solution number one. So what the obvious thing that you could do, you compute the distances of training samples with the test sample and take closest k training samples, just closest k based on the distance values. Okay. Now basically you can use that samples to build your linear regression function. The solution 2 is that we use a smooth weight function that will automatically downplay the role of distance samples. Okay, two broad solutions. Now, which one will you prefer? If I seek your opinion on this, solution 1 or solution 2?
Sir, can you explain solution 2 once?
Okay, solution 1. Solution 1 or solution 2?
Solution 2.
Solution 2. Okay. Solution 2 is that we are not putting any like parameter here, like okay, I am going to take k training samples. Okay, closest to the test sample. I am not doing that kind of thing. Not any hard limit on that. But rather, I would like to use a smooth weight function that will automatically downplay the role of distance samples. So my weight function, because you are computing the distance between the training samples and the test samples. Okay, now what you really want to do, you do not want to use the samples which are far apart from the test sample to contribute to your learning. That you do not want to do. Okay, so the idea is that whether we can use a smooth weight function, the nature of the weight function is such that it will automatically downplay the role of distance sample. So if the distance is very high, the weight function will tell the value is 0, something like this. Okay. So which solution you would prefer? Solution 1 or solution 2?
Solution 2, sir.
Solution 2.
So any particular reason for that?
Solution 1 takes most time, sir, whereas solution 2 takes less time.
Okay, so your suggestion is on time, that you were saying solution 1 will take more time, solution 2 will take less time. Okay, all right. Any other suggestion?
In solution 2 is more generalized.
Solution 2 is more generalized in what sense?
Sir, memory. Sir, I think memory, we have to store all that data, like when we are predicting.
So you are in favor of solution 2 or solution 1?
So solution 2 I'm in favor of.
You are in favor of solution 2. You are saying that it will not take more memory than solution 1.
Yes, sir. Memory optimization.
Okay, all right. Any other solution? Any other explanation?
So because in solution 1 we will have to select some like measuring distance metrics that about how we will measure the distance that samples are close or apart. So that is also a challenge.
But that distance also you will need to compute in solution 2 as well, because distance is the only thing. Distance or similarity, something like that.
Like distance
Sir,
metric, like how we are computing distance between points, this thing.
sir, in solution 2, we are not completely ignoring the other training data. But in solution 1, we are ignoring all other data other than those k closest. So maybe second solution will be a better option.
Okay.
Solution 1 is a subset of solution 2 only. So we can generalize a function in solution 2.
You can generalize the function in solution 2.
Sir,
Okay.
I have a
Because
question.
it's just the function here, the function that the smoothing function, if we call the function to be taking the k nearest neighbor, it's just solution 2, but we just change the function to make it solution 1.
Okay, now let me.
Sir, actually, I have a question, sir.
Yeah, sure.
Yes, like what if we have a test sample where, say, only there are 2 training samples near it, close to it, and but then if we go to solution 1, we have to take like 5, let's say k is 5, then we'll have a very bad solution, right, for that sample.
Right. Right.
So in that case, solution 2 is better. I mean, I'm saying.
Yes.
Like
So
having
definitely in this case, solution 2 is better. Yeah.
So also the k parameter in the solution 1, it's a completely random parameter. So we'll have to have some justification for what value of k we are choosing. So instead of that, we can just use one single function in solution 2, and also it captures the gist of the trend, and also it focuses on the local point that we have to test.
Okay. Okay. Any other explanation? I can sum up the discussion, but before that, if you have any other explanation.
So in solution 2, if in solution 1 we are ignoring every training example which is let's say some x distance away, more than x distance away, if there is disturbance in that data in those area of training samples, that will give the test result, make wrong predictions about it. But in solution 2, the disturbances would be ignored a little, because we are even seeing the data which are far apart. They have less weights, they have less value, but still they have some influence on the prediction. So that is a better way.
Solution 2 is better way.
Yeah.
Yeah. Okay. Yeah. So yeah, let me just sum up the discussion. So one is that obvious difficulty for solution 1 is setting the right appropriate value of k, which is very tricky. It depends on the sample and changes from one sample to another sample. That's first solution, first problem. And of course, yeah, second problem, and more, I think this more interest. I mean, I would say more critical problem that somebody mentioned is that when you put hard limit on k, say 10 or 20 or something like that, even a particular training sample which is far apart from the test sample, it may get included into your training data set for parameter estimation. Okay, because you are not putting anything on based on the similarity. You are basically putting constant on the number of closest sample. So very point which is very far apart from the test sample may be included into the set, which can distort the learning process. So yes, you are right. Solution 2 is the preferred solution, because the weighting function, even though it is going to include distant samples, but the weight factor is going to downplay the role of that particular sample. So in a sense, balancing act it is doing. So yes, you are right. All right. So remark is that essentially, so what we discussed, so that was a remark that solution 2 is considered better, okay, compared to solution 1. Okay. Right. But solution 1 can also be useful. I'm not saying good, but can be useful if you have extremely dense data set. So if you have very dense data set, okay, then points are very close to each other. And so if the training sample, the test sample that you are basically choosing is from a very dense region, then solution 1 also is a good option compared to solution 2. Okay? That's a possibility. But for sparse data, solution 2 is going to be better than solution 1. Right. So again, so same old business that we know that what we have to do, but then again we have to define the corresponding error function, because error function is the backbone of machine learning algorithms. Okay, so that basically going to tell you that how well you are actually doing. So error function. So what will be error function? Now let me just contextualize the whole thing by comparing the error function with respect to the linear regression. So linear regression, you know, this is the error function. Okay, ET is equals to the sum over all the errors on individual samples, that you know. But for locally weighted linear regression, same thing. One additional thing that we have basically introduced, which is called WI. Okay, what is the WI? WI is the weight that we have been talking about, this weight in the last slide. The weight of the ith sample. Okay, so we are just including that. WI is the weight of the ith training sample with respect to the test sample. Okay, so this WI is basically going to influence the learning process. So I'm going to discard the influence of the samples which are far apart from the test sample. Okay, and so again you have the same old business. You want to minimize ET, total error, using some kind of approach, some optimization technique, gradient descent or something like that. Okay, so that's what we really want to do.
Sir,
yes, please.
So like on what factors does that weight function depend on WI?
So weight function only depends on the distance between the test sample and the training sample. So in the next slide, I have the mathematical expression for that, but just to answer your question, yeah, so only distance between test sample and training sample.
So how do we actually define what the error function should be? Like, why is it not the absolute value or the fourth power or the sixth power? Why only the second power?
Well, I think you can also take absolute values, no problem. So one reason you are taking this one, so see when you are, it depends on the optimization algorithm that you're using. Okay, so there are many things in a machine learning. So in this case, if you are applying gradient descent, which is basically a standard thing to do, so better if you have smooth continuous error function. So if you take the absolute value, this is non-continuous, but I'm not saying this is going to be a problem, because nowadays people also optimize using gradient descent and non-continuous function as well with finite number of discontinuity. That's also possible, but this is much more convenient because this is now you have a continuous function. Because gradient descent will require computation of derivatives and all, so it's just easy to deal with.
So we take the error function to be sum of squares because it because the error is Gaussian, isn't it?
Well, I think that's basically very strong assumptions. Okay, it depends on the kind of data that you have. Okay, so you can say often probably it's a Gaussian, but that has nothing to do with this particular function.
So actually, if we assume the error to be Gaussian and we derive the and then we derive the optimization, if we minimize the L function and then we get that we have to minimize the this least square error.
But why you want to make this assumption about the Gaussian? Well, without Gaussian, you can still do good job.
No, sir. I'm saying if we assume, then we get it. Then we get that we have to minimize this least square error function. But the other way, I mean, it need not be true.
Yeah, that's right. Yeah, but better if you so sometimes in building a machine learning models, if you assume a particular you make a particular assumption, that simplifies the model construction and all. But here, at least for optimization purpose, we do not need to make that kind of assumption. Okay, strict assumption. If it follows, that's all right. That's good. But you do not need to make that kind of assumptions. Okay, so yeah, so this only difference is basically the introduction of WI. Let's see now, actually we can compute the WI in the next slide. Okay, so now again, so in machine learning always, like first of all you have to be very clear about what your objective would be. Okay, once you know your objective, then you can, it's all playing with functions often, right? So once you know your objective, then you can come up with functions nicely. So the question is how to compute WI, and you recall the objective. The two objects we have, we want to reward samples closer to the test sample, and we want to punish samples far away from the test sample. So we have to construct the function wi in such a way that we basically satisfy these two conditions. Okay, that's the essential idea here. Okay, so here is one such thing. Okay, so wi is equals to, which is basically also is a Gaussian kernel. Okay, so yeah, so radial basis function actually. So e to the power of minus, the denominator is the distance, the Euclidean distance between ith sample and the test sample, ith training sample and the test sample, and the is a numerator, sorry, and the denominator is basically 2 into c square. C is is a pre-parameter, okay, which will control this whole thing, scaling parameter actually. Okay, so this is the kind of this function that we use to achieve these two conditions that we mentioned. Okay, and C is a pre-parameter, is a positive parameter, which is hyperparameter. You have to basically do some kind of validation to choose what is the good value of C. Okay, now you can quickly verify that is actually satisfying these two conditions. Okay, conditions mentioned in point 1 and point 2. So if xi and x test are very close, then the distance becomes close to 0, then wi is close to 0. Okay, if the xi and x test are very far away, then the numerator becomes very large, and so wi is tends to basically 0, close to 0 actually. Okay, so that essentially satisfies these conditions. You can take other functions as well. There is access, but this works pretty well at least. Okay, that's the empirically people have actually shown that this works pretty well. Okay.
So, but what if we just ignore C? I mean, if we just remove C and just use the distance.
Sorry.
And what if can we just ignore C, right? We can also ignore C and then won't that be weight function?
I don't. C is basically you can smooth the values. Okay, it's just you can think about the scaling parameter, smoothing parameter. If you ignore C, it may be difficult to kind of get good results. Okay, because there are several reasons of that. Number one, these values. Okay, the numerator value will depend on the number of features that you have in your data. Okay. Now the absolute values of this feature, the range of these features, and also on different kinds of applications and so on and so forth. So C in a sense will regularize all these things.
Okay, sir, got it.
Okay, so it may vary from one problem to another depending upon the dimension of this data, distribution of the data, and so on and so forth. But if you completely ignore these things, then you basically are making that you are assuming that everything will be fine for all kinds of data, and that I think is a very hard assumption. Okay, so I will stop here today because it's already 11:53. If you have any question, please feel free.
The smooth weight function in the solution will have same weight form.
Sorry, say again.
So the smooth weight function that we discussed in the solution 2 in the previous slide. So
right.
We will use the same formula as we use in the error function, the same weight formula.
Yeah, so here this wi is you are comparing this weight for the sample with respect to the test sample, and then basically you use that here. Okay.
Okay, we are calculating error function in that, but yes. We told one smooth weight function, right, in the solution 2.
So that smooth weight function is wi. Right, so I think you are referring to this solution number 2, right?
Yes, sir. Yes, sir.
So this solution number 2, I am actually this expression is based on solution number 2, the number 2, point number 2. Okay. And here the wi in particular, that's smooth weight function. Okay, so we are computing using this expression. So essentially, I am encoding this the solution number 2 which we discussed.
And sir, how will we get this scaling parameter?
Well, I think C is this is hyperparameter and standard approach that there is no good recommendation how to do it apart from doing some kind of cross validation on a data to try to figure out what the good value.
And sir, if it will be a constant, then why here you have it is C square? Means what is the significance of doing a square of a constant?
Well, I think you can avoid. Yeah. This is just the nature of this Gaussian function, okay, this radial basis function. But you can avoid, you can replace C square by some other things.
Okay, sir.
Sir, I have a request regarding the big data class. Can we have 8 members in a group?
I already responded, I think, to. Yeah, please go ahead and do it because it's already become very large. So.
Okay, thank you, sir.
Okay, so any other question? Okay, so thank you all for joining, and we'll see you tomorrow morning. Okay, thank you.
Thank you, sir.
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 Thank you.